Hello again, this is Module 7 of Geography 385. We're talking about the raster model. Last time I covered a lot of the basic concepts with raster model. I had covered this back in week 1. It was a refresher. Today I'll do some more review and then maybe add some things that I haven't talked about yet for raster model. If I can get my page down key to work. Okay, each cell represents an area on the ground. So larger cell, larger area, smaller cell, smaller area. Each cell gets one value, a single value that covers all of the ground covered by that cell. So if the value inside of that cell is uniform across the cell, then you have an accurate cell. But that's frequently not going to be the case. In continuous phenomena, the value is actually going to change within that cell. So when the value changes within the cell, and you can only store a single value, how do you store a single value? Well, sometimes you use the most common value if you have multiple measurements within a cell. Sometimes you average values. Sometimes you do some other statistical measure of the values within a cell and use that statistical measure. It all depends upon the model and what aspect of reality you're interested in. Okay, each cell is assigned a single or maybe no data value. So no data, remember, is just a special value the computer uses to tell the computer that there's no data for that cell. So here we have a 10 meter by 10 meter cell, square cell, and you can imagine that there might be a measurement that was taken somewhere inside of that cell. And the entire cell is going to be assigned the value of that point. But in general, what you can think of cells as points that are at the center of the cell. So there's going to be a positioning issue with measurements that are taken within a cell that don't actually fall at the center of the cell. Sometimes you have multiple measures within a cell, and you have to only assign one value to the cell, so depending upon how you're going to do it, the most common value, average, things like that, you're going to take that single value, store it for the entire cell, but conceptually it's basically a point at the center of the cell. So what kind of values would you store in these rasters? Well, this column talks about different types of data you might store in these rasters for cell values. An example of a point ID might be the nearest hospital. So in any cell of a raster, there might be a number that's associated with the hospital that's closest to that cell. Same with a line ID. For a line, any cell might have a number for which road is nearest that line. You can see where it would apply to polygons. You might have numbers in cells, and the number in the cells represents the state that that cell is within, or predominantly within. These, you notice, are all categorical data. They're nominal data. When you get further down, there are some numeric data, which would be the interval or the ratio data. And one example is the National Elevation Data Set. And that's a data set I'll talk about in the next video, which is a raster data set that you can get that represents the elevation above mean sea level of all of the continental United States. And so that's going to store a numeric value in the cell, but it's not going to be an integer. It's going to be a decimal numeric value, and it's going to represent elevation. Cells are most often square-shaped. I talked in the last video about how you have to be careful with cells that are in geographic coordinates, because the cells that you get from geographic coordinates, latitude and longitude, are going to depend upon the latitude, and so they're not going to be square-shaped. And you need to make square-shaped cells if you're going to do analyses, so you need to make sure you project your geographic rasters to a projected coordinate system if you're going to do an analysis. You specify the cell size as the length of one side of the square. Since you're assuming it's a square cell, or you'd like it to be, your cell size is specified as the length of one side. If you have different sized sides, then you'll probably use an average size as the average cell size. So when you think about this, higher resolution, better resolution, is smaller cell size. The finer the cell size, the better resolution. So smaller cells, higher resolution. Here's an example of what you can think of as a large cell, and it has the value of 7 in it. Now that large cell may have been made up of smaller cells, higher resolution cells, and in this case these 4 cells were smaller cells that were aggregated into this larger cell. So if I add these up and divide by 4, I can see that I took the average value of the smaller cells and assigned it to the larger cell. And this is equivalent to generalization in raster data sets. So you can generalize smaller cells into larger cells, and that sometimes is called resampling, smaller cells to larger cells. Higher resolution, smaller cell size. Here we have a 30-meter satellite image. It's a raster. The value of the cell is a value that's assigned to the color that's displayed there. And you can see that it's pretty pixelated and not really very good resolution. If you want to get better resolution, you can use smaller cells. In this case, you go down to 1 meter and you can see you get better resolution. Higher resolution is going to require more computation and more storage space. Smaller cells, more numbers to store. It's going to take more to store it, and it's going to take more time to compute. Here we have 4 cells, 100 meters across. Let's say we want to double the resolution, so we want 50-meter cells. Now instead of it taking 4 cells to represent our area, we need 16 cells. What if we want to go down to 25-meter cells? That's going to take 64 cells. So if we want to quadruple the resolution, go from 100-meter to 25-meter resolution, we've got to increase the number of cells by a factor of 16. So if we increase the resolution by a factor of x, so in this case 2, factor of 2, and then another factor of 2, we have to reduce the cell size by 1 over x. So 100 meter gets reduced to 1 over 2 times 100 meters, 50 meters. And in order to do that, it's going to take 2 to the x more storage space and more computation time. So finer resolution, more storage, more computation. I've already covered this georeferencing. The way it works is you assign coordinate values to a corner of your grid, and then each individual cell is identified by offset in terms of number of cells in the x and y direction. Attributes. So over here we have an integer raster. So these are integer values. And you can see where maybe 4 represents some phenomenon. I don't know what that might be, a river or a road or something like that. This might be a house, something like that. So each pixel has a value. When you have integer rasters, you can get what's called a value attribute table, and that's what this is right here. And what the value attribute table is it looks at all the unique values that are in your raster, in this case 1, 2, 3, 4. It counts the number of cells that have each one of those values, and it gives you a column called the count. Okay? So theoretically you could add up all the counts, and that would tell you how many cells were in your raster. However, there are no data cells in this raster, and you see that no data doesn't appear in the table. So be careful if you're going to try to use count as a measure of either area or number of cells. Okay, so if we have these values and they're integer values, we might have other non-spatial data in a spreadsheet or something like that, and just like in the vector model, we can join the aspatial or non-spatial data to the spatial data if we have a common value in the two tables. So we're able to actually attach attributes to a raster if it's an integer data type. This part, the value attribute table, is calculated automatically. This is one where you would have to join it, supply that table, make the join. And remember, no data cells aren't included in that value attribute table. How do we store these things? We store them in raster data sets. Everybody remembers from the vector model we had feature classes and feature data sets. In raster we're going to store things in raster data sets. A data set in raster is different than a data set in vector. Raster data set is data in any of many different formats, a bunch of formats. Any image format that you can think of is a raster format, organized into bands. So data sets are made up of bands. Each band is a grid that has the cells. So grid with cells equals band, multiple bands equals data set. And then of course each cell has a value, or it has the no data value. In ArcGIS, there's 3 basic ways we store these things. We can just use them as files. We can have TIFF files or PNG files or JPEG files. The Esri standard format is called an Esri grid. There are a bunch of other formats that have evolved over the years, so there are just countless numbers of raster formats. We can create a geodatabase and store the rasters inside the geodatabase. But remember that rasters frequently take up a lot of storage space, and so you need to be careful with geodatabases and storing your rasters in the geodatabase. A third option is we can store the files in their own separate file system, and then we can have a geodatabase that has references or pointers to those files. So we can make a geodatabase which is like a directory of the files and where they are and what they are. We can work from the geodatabase and access the files that aren't actually stored in the geodatabase. There's a higher level data set called a mosaic data set, and that's a collection of raster data sets. So a data set can be a collection of bands, and a mosaic data set is a collection of data sets. For mosaics, things don't have to overlap. They don't have to be the same time. They don't have to be the same cell size. They don't have to be the same anything. They can be captured on different dates. They can have different projections, resolutions, data types, number of bands. We can put them all together and we can manage them as one giant raster. And that way we can display pieces from this mosaic of rasters as a single raster using ArcGIS. We store the information about the data sets in a geodatabase, but it's only references, it's pointers to the other places that those rasters are stored. Okay, next time I'll talk about a few of the common raster data sets that are in use out there that you can get from the government. You can get elevation data sets, you can get precipitation data sets. I'll just talk about that next time.